Welcome back to College Algebra. In this video, we're going to be looking at exponential functions and modeling applications which use exponential functions. So without further ado, let me get my head out of the way and let's dive right in. Exponential functions, when you first encounter them, are often confused for power functions, both of which involve an exponent. Power functions that you've seen before are functions in the form f of x equal x to the n for some constant n. The squaring function, the cubing function, things like that. In an exponential function, instead of having a variable raised to a power, we have a constant base raised to a variable power. So a raised to the x power. And you can evaluate most exponential functions the same way you deal with any other exponents. Your calculator is happy to help you out. We do know some weird things that happen with the fact that exponents are really, fractional exponents are really radicals in disguise. So note, for example, that a to the 1/2 power is the square root of a. Which is not defined for a less than 0. And note that 0 to the x is equal to x. No. 0 to the x is equal to 0 for any x, which is very boring and not interesting. So we insist that we deal with an exponential base a, which is greater than 0, in order to call it an exponential function. The base of 0, like I said, is boring. Negative bases tend to break things at random places. And breaking things at random places is a little bit annoying, so let's skip that. All right. So taking an interesting value, y equals 2 raised to the x power. A couple of things that you should notice about an exponential function. The first one is that 2 to the x is going to be strictly greater than 0 for all values of x. No matter what number you put in, if you take a positive number and raise it to some power, the result is going to be positive. If you take positive values of x, you're going to get larger and larger and larger numbers. If you take negative values of x, you're going to get smaller and smaller and smaller numbers, right? 2 to the negative first is 1/2, 2 to the negative second is 1/4, 2 to the negative 10th is 1 over 1024, and so on. A couple of other interesting values. 2 to the 0 is 1, 2 to the first is 2. And we can make these same claims for any exponential function. No matter what base you are using, since we are insisting that the base is positive, raise it to any power, it stays positive. and anything to the 0 power is 1, anything to the first power is that thing. So that gives us some information that will help us graph the function. All right, so 2 to the 0 is 1. Here's 0, 1 on my graph. 2 to the first is 2. Here's 1, 2 on my graph. And my goal is to draw a curve that goes through these and never crosses the x-axis. Because again, remember, values down here would be negative. And we know that 2 to the x must be greater than 0. So we need to be above this and then head upward. And the way to ensure that is to have a horizontal asymptote at y equals 0. So we're going to come along the asymptote. We're going to go through those points. We're going to continue upward in a very fast growing path. And that gives us the basic picture of what this graph should look like. Playing around with transformations on graphs, two transformations that are most common in exponential problems. Well, y equals negative 2 to the x. A negative in front would cause us to flip the graph vertically. I'm not going to be very careful drawing this out, but you get a curve that would look something like that. And y equals 2 to the negative x, a negative inside the argument of a function we've seen. Causes the graph to flip horizontally. So instead of curving upward, again, I'm not being particularly careful here, but you would get something that curves upward to the left and downward to the right. Now, one interesting thing I want to point out is that 2 to the negative x power, using properties of exponents, is 2 to the negative 1 raised to the x. And 2 to the negative 1 is 1/2. So another way you can think about negative exponents or negative arguments in an exponential function is that it takes the reciprocal of the base. We go from 2 to the x to 1/2 to the x. Another way of thinking about that, if your base is bigger than 1, it will grow to the right and have a horizontal asymptote to the left. If your base is smaller than 1, it will grow to the left and come to the horizontal asymptote as you go to the right. Keeping those couple of things in mind can help you draw these graphs. You can also just focus on thinking about where those key points went and remembering that there's going to be a horizontal asymptote, and that can generally get you a pretty good picture as well. When working with exponential functions, it turns out that there is one particular base that makes a lot of work significantly easier than it would be otherwise. The reason why it makes everything so much easier is something a little bit beyond the scope of this course. Those of you who are moving onward to take calculus will experience some of the fun there, often in the second semester of the calculus sequence. But we call that base the natural number. And it has a very interesting definition. The natural number is defined as 1 plus 1 over n raised to the n power. As you take bigger and bigger values of n, this thing starts to become a nice, easy to work with. Well, easy to work with might be stretching it a little bit, but it becomes a nice repeating pattern. All right, starting with n equals 1, we have 1 plus 1 over 1 to the first power, which is 2. If n equals 2, we have 1 plus 1/2 squared, which is 2.25. If I take n equals 5, that will be 1 plus 1/5 to the 5th power, which my calculator tells me is something that starts 2.488. And we can keep going from here. I'm going to start really jumping things now. N to the 10th, when n is 100, and when n is 1000. So we have 1 plus 1/10 to the 10th power. Which my calculator tells me is approximately 2.594. 1 plus 1 over 100 to the 100 power, my calculator tells me is 2.705. 1 plus 1 over 1000 to the 1000 power, my calculator tells me is 2.717. And at that point, the progress starts to slow down a little bit. As you get bigger and bigger numbers, you'll get closer and closer to what we call the exact value. We've named this natural base E. It's named after the mathematician Leonard Euler. And essentially, about a third of everything in mathematics is named after Leonard Euler in some way, shape, or form. So it's not really too much of a distinction, but sometimes this is called Euler's constant. And it is an irrational transcendental number, much like pi. Decimal approximation continues onward without repeat, but it starts off 2.71828 and continues from there. You do not need to memorize Euler's constant because it's programmed into most calculators. And in fact, it's programmed into calculators in the most effective manner possible because we use it as the base of exponents. It's programmed in as an exponential function. On my calculator, I have a natural log key, which we'll be talking about in a few minutes. And if you look above the ln key, it says e to the x. And that's what I'm looking for. So if I want to evaluate e to the 3.7 power, I can hit the e. It automatically puts in the exponent for me. I can just punch in 3.7. I can tell it to evaluate, and it spits out that the answer is something that starts 40.45. Right. Where the exponential key is hiding on your calculator will vary, but take a few minutes before you continue onward to look through your calculator, identify where that key is, and make sure that you are able to evaluate this function as well. As I said, the natural number shows up very frequently in modeling applications. Specifically, we're going to be looking at the situation of exponential growth and decay models. To be even more specific, usually we drop the word continuous from this name, but we are specifically going to be looking at continuous exponential growth and decay. Exponential growth and decay can encompass things that are not growing continuously, called discrete exponential growth and decay, which we are not interested in this course. But a continuous exponential growth or decay model is anything that can be calculated using an equation in the form A equals P times E raised to the RT power. Capital A is the amount that you have at the time in question. So exponential growth is going to start with a small amount of something and grow to be larger and larger. Exponential decay is going to start with a large amount of something and grow to and shrink to become smaller and smaller. P is the amount you start with, and A is the amount you end with. Little r is a thing we call the growth rate, and little t is the time. The reason that we use the letters A and P when talking about this is that one of the key applications of exponential growth and decay is compound interest. When you invest money in a savings account, the amount that you invest is called the principal, P, and you can use exponential growth and decay with your interest rate as R to calculate how much your account will be worth after a certain amount of time. Exponential growth and decay is also incredibly useful in talking about growth of bacteria, or more generally, growth of cells in a culturing nutrient auger or something like that, where the number of bacteria you start with would be P, and the number of cells of bacteria that you have after a certain amount of time would be A. The other classic example of exponential growth and decay is the idea of radioactive decay of nuclear radioactive materials. Right? So as radium decays into radon and emits nuclear radiation, these exponential growth and decay formula will help you figure out how much radium is left after a certain amount of time. When you're talking about exponential growth, we get a positive value of r. When you're talking about exponential decay, we get a negative value of r. Sometimes you will see this formula written with that negative sign baked in. Generally, I don't do that, and I just try to keep in mind, I'm talking about decay, I need to make sure I put a negative sign in there. So as an example, let's suppose that $1,250 is invested at 3.5% continuously compounded interest. We want to know what this investment will be worth after 12 years. So we're talking about continuous growth, continuous exponential growth and decay. We're looking at the formula A equals PE to the RT. A is our unknown. P is 1,250. E is Euler's constant, which we'll just leave as E and let our calculator handle that. R is 3.5%. But as you have frequently seen throughout your study of mathematics, even though percents look like numbers, they are not numbers. So to do calculations with them, we have to convert from 3.5% to 0.035. And then T is 12. And I can punch that whole thing into my calculator, which was supposed to be displaying on the screen, but apparently my camera's not working today. I fix one camera, I break the other, I apologize. But when I punch that into my calculator, I get a horrible, ugly number. Since this is money, I think it makes sense to round to the nearest penny. And I get $1,902.45. Much in the way that we use the radicals as inverses of power functions, we need a tool for the inverse of an exponential function, and we call that tool the logarithm. Right? So we have f of x as x to the n, a power function, and the inverse, f inverse of x, is the radical function nth root of x. Another way we have written that is if y is equal to x to the n, then x is equal to the nth root of y. And we want to do the same thing with exponentials. If we have a function, f of x is some base b raised to the x power, then we want an inverse function. And to name this inverse function, as I said, we call it the logarithm, and we simply write it as log with a subscript b for what base we are talking about. So if f of x is b to the x, the inverse is going to be log base b to the x. And again, another way of writing that, if y is equal to b to the x, then x is equal to log base b of y. There are logarithms for literally every base, just like there are radicals for every power. And logs are not created equally. There are a couple of logarithms that are far and away the most useful. Depending on what you are planning to do, will change which of these logarithms is important to you. But the common log, which is simply written as log of x, is the log base 10. So if we suppress the base name, then what we're talking about is the log base 10. The natural log, which is going to be the one that sees the most use in this course, is written as ln, and it's the log base e. And the last one, which I want to mention the name of, is the binary log, lb, or log base 2 of x. The binary log is incredibly useful in computer science and computer programming. Unfortunately, on most scientific calculators, the binary log is not programmed in. So even though if you are going into computer science, the binary log is going to be incredibly important, we're not really going to look at it in this course because it's inaccessible to most students on most scientific calculators. Evaluating logarithms is practically impossible by hand. In some special circumstances, we are able to do so. For example, if I want to calculate the log of 100,000, well, I know that 100,000 is 10 to the 5th power. And I know from the definition of common log that y is equal to the log of 10 to the 5th power if 10 to the 5th is the same thing as 10 to the y power. And by playing a simple matching game, we see that it must be the case that 5 is the value of y, so the log of 100,000 is 5. If you cannot do that, and generally you cannot, instead we will use a calculator. And most calculators have a common log and a natural log feature built into the calculator. So before we get any further, I would like you to grab your calculator and calculate the common log of 273 and the natural log of 157. Rounding to a reasonable number of digits, the common log of 273 should be something in the ballpark of 2.44, and the natural log of 157 should be something in the ballpark of 5.06. Again, rounding both of those to the nearest hundredth, just to round them somewhere. With very few exceptions, the common log or the natural log or the log of any other base of any given number is an irrational, transcendental number and unpleasant to try to write out. So we use decimal approximations. All right. So now that we are able to calculate common logs and natural logs, it's time to press onward and start thinking about how logs work. And I'm going to use the approach of analyzing a graph. And let's pay attention to the natural log because it's going to be a little bit more useful to us this semester. We know how to graph an exponential function. Graphing y equals e to the x is a little bit tricky because it is irrational values. But we know that for any exponential function, it's going to pass through the point 0, 1. And it's going to go through the point that is 1 and the base. In this case, the base is 2.71. Which is somewhere in the ballpark of right there, the way I've drawn this graph. And I just realized that the tick marks I drew didn't actually show up. So let me put those in again so you can actually see what the scale is. That looks a little bit better. So we have the points 0, 1, we have the point 1e, and we have a horizontal asymptote at y equals 0. So kind of trying to sketch in gives us a curve that looks something more or less like that. So since the natural log is the inverse of the exponential function, graphing a natural log, we simply want to swap the x and y coordinates of our key points. So the point 1e is going to swap to be the point e1. The point 0, 1 is going to swap and become the point 1, 0. And the asymptote, which was at y equals 0, is going to swap x and y and become the vertical asymptote, x equals 0. And that's exactly what the graph of the logarithmic function, the natural log in this case, ends up looking like. So we plot our points. E1 is somewhere about there. 1, 0 is somewhere about here, and a vertical asymptote to follow along in gives us a curve that looks something kind of like that. And just by looking at that, we get a lot of detail about what the natural log or what logs in general should be doing. The domain of a logarithmic function goes from 0 to infinity. which makes sense because in the exponential function, the range went from 0 to infinity. The range of a logarithmic function should be all real numbers from negative infinity to positive infinity, which makes sense because in the exponential function, the domain was all real numbers, negative infinity to positive infinity. So we have some idea now of what the logarithmic function looks like. And with that, we can start using the logarithmic function to solve problems. Just like we used the radical function to solve equations involving powers, we will use the logarithmic function to solve equations involving exponentials. So if you have an equation like e to the 7x equals 12, we can convert from an exponential equation to a logarithmic equation using the definition of the inverse function, e to a power equals 12, if and only if that power is the natural log of 12. And my calculator is happy to tell me that the natural log of 12 is 2.48 or somewhere thereabouts. Pay attention to instructions on rounding. I'm rounding in this video to the nearest hundredth, but problems in the homework and problems on exams will have specific instructions for you as to how to round. But then from here, to get x by itself, we of course divide both sides of the equation by 7. Which comes out somewhere in the ballpark of 0.35. If there is more going on in the equation, sometimes it takes a little bit of work before we can use that change from exponential to logarithmic. If we have something like 3 plus 5 e to the negative 2x is equal to is equal to 4. Well, before we can solve for x using the logarithmic function, we have to get this to look more like the problem we solved before, which means we have to get this e to the negative 2x by itself first, which is not too bad. Subtract 3 from both sides of the equation. Then divide both sides of the equation by 5. And we get that e to the negative 2x is 1/5. Now this looks like the equation we solved before, so we can solve from here using the same process. If e to some power is equal to a constant, that power is equal to the natural log of that constant. That's the definition of log as the inverse of an exponential. My calculator is happy to tell me that the log of 1/5 is negative 1.61. And if I divide by negative 2 to get x by itself, I get that x is 0.81, somewhere thereabouts. And with that, we have the tools necessary to go back to the exponential growth and decay problem and answer some more interesting questions. So consider an investment account which earns 2.9% continuously compounded interest. We ask the question, how long will it take for this account to double in value? And at first glance, it feels like there's not enough information to solve this problem. Because we know that whenever you're talking about exponential growth or decay, you're going to look at a formula like A equals P times e to the RT. And in this problem, we know that R is 2.9%. So we get A equals P times e to the 0.029 times T. But there's one other thing we know about this situation. It tells us that we want the account to double in value. It doesn't tell us where we want the account to start. It doesn't tell us where we want the account to end. But it does tell us that we want to look at the place where the value is 2 times where it started. So we have 2p equals p e to the 0.029t, and we can divide both sides of the equation by p to get 2 equals e to the 0.029t. This is exactly the kind of equation that we were just looking at. We have some constant equals e raised to a power which contains the variable we want to solve for. So using the same process we used before, if 2 is equal to e raised to this power, the natural log of 2 is equal to the power itself. My calculator is happy to tell me that the natural log of 2 is something like 0.693. And if I divide both sides of the equation by 0.029, I get 23.9 as the value of t. It will take just shy of 24 years for this investment account to double in value, given the amount of interest that it earns. If the investment account earned more interest, a higher interest rate, then it would take less time to double. There's a lot more that you can do with exponential and logarithmic functions. The point this week is just to give you a taste of the power of these things. Moving onward from here, you will most likely encounter exponential and logarithmic functions in another course and learn some of the other techniques that you can use, some other problems that you can solve just by using the same basic tools. With that, I'm going to wrap up here. Thank you as always for joining me, and I'll see you next time.